So today we're going to look at lesson 3-2, which is multiplying and dividing radicals. So a radical expression with index n is said to be in simplest form if there are no radicals in any denominator, no denominators in any radical, and any radical has no nth power fractions. So we're going to get more to that in a minute, but let's do an example. So for example, if I had the square root of 48. 48 can be, since it's a square root, I'm going to convert 48 into its prime numbers. So 4 2's and a 3. So just prime factor it. And because I'm looking for groups of 2, I've got 2 groups of 2. So I can take out in front of the radical 2 2's, and then this 3 is left underneath. Square root of 3, which then you got to multiply what's in front. So 2 times 2 is 4, radical 3. So this would be a fully simplified radical. If you rewrite the denominator so that there are no radicals in any denominator and no denominators in any radical, this process is called rationalizing. So that's another thing we're going to look at today. The denominator. So for example, let's say that I had 2 over the square root of 3. You cannot have a radical in the denominator. So because it's a square root, how many more 3's do we need to make this a perfect square? Well, I have 1 3. I need 2 3's underneath that radical. So I would multiply the bottom by the square root of 3. Whatever I multiply the bottom by, I have to multiply the top by. And you will find out that you can only multiply what's outside of a radical to what's outside and what's inside to what's inside. So that the numerator will become 2 radical 3, and the denominator is radical 3 times radical 3, which is the square root of 9, which is 3. You take a square root times itself, and you always get the number under the square root. And so that would be the process of rationalizing the denominator. So then for our products, basically we're going to use the following procedures. So you have to have the same index. So let's say I had the nth root of A and I'm multiplying it to the nth root of B. I can only multiply 2 radicals that have the same index. If they do have the same index, then I can put them underneath the same radical and multiply them together underneath. Same thing with quotients or division problems. I can divide 2 radicals as long as they are the same index. So if I had the square root of the nth root of A divided by the nth root of B, because they both have the same root, I can put them both underneath the same radical. So it'd be the nth root of A divided by B. So let's look at a couple of examples. So the question is, can you simplify the product of the radical expressions and then explain? So for part A, the answer is no, because they do not have the same index. So yes, they have the same radicand, but I can't multiply these unless they have the same index number here. So your answer is no. They have different indexes. So your indexes must be the same. All right, then look at B. So for B, they have the same indexes, so we can multiply them. So then we're going to take -5 times -2 So we've got the fifth root of negative 5 times negative 2, which is the fifth root of 10. And you cannot simplify that any further, so that would be your final answer. Look at C. This time, we have the same indexes because they're both square roots, but the problem is this is a negative. You cannot take an even root of a negative value. You don't get a real answer. So although you can multiply them, you just can't simplify them. So for instance, they have the same indexes, so I can multiply what's underneath, and I would get the square root of negative 12, but the question is, can you simplify this? And the answer is no, you can't simplify. There is no real root due to that negative underneath the even index. We will talk about how we will take the square root of a negative number later. All right, so let's look at some radicals and put them into simplest form. Let me make this really big so everybody can see it. Okay, so there are several different rules of thumb to doing this, and I've argued with teachers over this many times, but in my opinion, you can break down this 96 any way that you want to. Because the index is 2, you can break the 96 down into perfect squares. If the index were 3s, you can try to break it down into perfect cubes if it had any. If that were an index of 4, you could break it down into, to the 4th power of something. I tend to find out that most kids will prefer to prime factor it all the way. And that's up to you. Depending upon how big the number is and how many prime numbers that number has, it could get really long. So let's go ahead and prime factor 96. So the numbers that divide into 96, I know for sure are 4. So 4 goes into 9 twice. Carry the 1 and into 16 4 times. And then 4 becomes 2 and 2. And 24 becomes 4 and 6. 2 and 2. And then 2 and 3. So I can rewrite 96 as the square root of, I've got 1, 2, 3, 4, 5 2's. And a 3. And of course we have this x to the 8th and y to the 5th. So because we have a square root, again, the index here is 2. So because we have a square root, we're going to be looking for groups of 2. So I have one group of 2. For every group that I pull out from under the radical, one number from its group will represent it out in front. Second group of 2, so I have a second 2 I'm going to multiply, and then these are going to be left underneath. Then you have to deal with your powers. We talked about those the other day. So if this index is 2, we're going to divide the 8 by 2 and the 5 by 2. Well, in the last lesson, when we divided the 8 by 2 and the 5 by 2, it went in there evenly. Well, today it may not. So in this case, 8 divided by 2 is 4. So 2 goes in there 4 whole times, so you are going to bring out an x to the 4th. There are no remainders, so no x will remain underneath the radical. However, here with the y, 5 is divisible by 2 twice, 2 whole times. So we are going to pull a y squared out because 2 goes in there 2 whole times, but there's one remaining y. Because 2 times 2 is 4, that leaves one y remaining out of the 5. That y is going to stay underneath the radical. So here's what we have left under the radical. We have 2 times 3, which is 6, no x's, and then we have a y. So I guess I can erase that part. And then you have to multiply anything out in front that you can multiply together. Well, I can multiply these two. So I end up with 4 x to the 4th y squared square root of 6y. And that's your final answer. Now we do have to pay attention to even roots and make sure that the answer that gets pulled out in front is going to be a positive value, because remember, this is indicating that I want a principal square root, meaning I want the positive answer. If you recall, all even roots have two answers, a positive answer and a negative answer, and this is asking for the positive one. So when you bring variables out in front of the radical, we don't know if the variable value is going to be positive or negative. So if x were negative, it wouldn't matter because 4 negatives are going to make a positive. If y were negative, it wouldn't matter because 2 negatives will make a positive. So if your exponent here are even, there's no problem. But if your exponent here becomes odd, then we're going to have to put absolute value signs around that variable with an odd exponent. And this only happens if you have an even index. Okay, so then let's look at B. So B is an odd root. You can take an odd root of a negative. So when I factor this out, I'm going to factor the negative out. So I've got negative 1 times 128, and then 128, I know 4 goes in there 32 times, and 4 is 2 and 2, and you need to get used to the fact that 32 is 2 to the 5th. There are 5 2's in 32. So that means that we have 7 2's altogether in 128. So as you can see, it can get quite lengthy to try to stretch all these out. So if you wanted to write 2 to the 7th underneath, that would be fine, and then you can use our power rule for the indexes. But to make some of you happy, I will continue. So the negative 1 we'll talk about in a minute, but then I have 1, 2, 3, 4, 5, 6, 7, and a b to the 7th, all underneath the radical. So because I'm looking at an index of 3, right here, index of 3, I'm looking for groups of 3. Well, technically I could write the negative 1 as negative 1 times negative 1 times negative 1, because that's still negative 1. So anytime you have a negative underneath an odd root, that negative is going to come out as a negative. I mean, and theoretically I could also attach a negative to each of the 2's, but I just didn't feel like doing that. So that negative is going to come out. Now, there are some people that will attach a negative onto each of the 2's, and then if you do that, your answer is going to be slightly different. You're going to end up with a negative underneath the radical. My negative is going to end up being outside. So we can argue that till the day is long, but it doesn't matter which way. So I'm going to take out that negative 1 as a negative out in front, and then I have one group of 3, and I have a second group of 3, and so then I'm going to have a2 left underneath the radical, and then I'm going to take the index of 3 and divide it into the 7, and it's not going to go in there evenly, but 7 divided by 3 goes in there 2 whole times. So I am going to have a b squared come out in front. 2 times 3 is 6. That's going to leave 1 b left over underneath the radical. So underneath the cube root, I will have a 2 and a b. So then multiply what's out in front. So these multiply to give me negative 4 b squared cube root of 2b. Now because we have an odd root, I don't have to worry about absolute value signs. Let's go on to example C. So then you need to stop the video. Go ahead and stop the video and try this one on your own. Meanwhile, I'm going to go ahead and complete it. Okay, so hopefully you did this on your own. If you prime factor 72, and then 8 has 3 2's in it. So we have the square root of, now you could have left the 2 as 2 cubed and apply the index rule. That's purely up to you. All right, so I have a square root, so I'm looking for groups of 2. So here's a 2 coming out in front and a 3 coming out in front. So that leaves a 2 underneath. Then I've got to divide by 2 and divide by 2, and that's going to come out nice and evenly. So 4 divided by 2 is 2, so I have an x squared. And 6 divided by 2 is 3, so I have a y cubed. And then underneath the radical, all we have left is a 2. And then we have to multiply what's out in front. So I have the 2 times 3, which is 6, x squared y cubed square root of 2. Now normally we'd be done, but remember this is an even index, and when I bring anything out in front, it has to come out to be positive. If x were negative, that wouldn't matter because a negative times a negative is a positive. But if y were negative, because of this odd exponent, we would have 3 negatives and it would end up making a negative out in front. So we have to put the y cubed in absolute values and only the y cubed. So this is your final answer. Then let's look at example 3, letter A. So now we're going to multiply. The mantra here is you're going to multiply, as long as the indexes are the same, which they are, you're going to multiply coefficient to coefficient, like base to like base. And when we multiply like bases, we add the exponents. Now I personally would not multiply 45 to 35. If I were you, I would prime factor 45. So we get 5 times 9 and 3 and 3. And 35 is 5 and 7. So underneath my square roots, I have 2 3s, 2 5s, and a 7. Then when I multiply like bases, I've got x to the 5th and x to the 1st. So 1 plus 5 is going to be x to the 6th. And then x to the 3rd times x to the 4th, if I add the exponents, I get y. Did I say x? I meant y to the 7th. So then I have a square root, so I'm looking for groups of 2. So I take a 3 out in front, a 5 out in front. Poor little 7 is going to be left underneath. Then apply your index rule. I'm going to divide by 2, divide by 2. So 6 divided by 2 is 3, and then so that goes in there fully, equally. Nothing left over. 7 divided by 2 is 3, so I get y cubed. But this time I'm going to have a y left over. So square root of 7y. Then I have to multiply the 3 times 5, so I get 15. X cubed, y cubed, square root of 7y. Now we have an even root, so we have to look to see, are these odd exponents going to create a negative if x or y is negative? And the answer is yes. If x is negative or if y is negative, it will create a negative. So I'm going to put both of those in absolute values this time. And then this is your answer. So then you pause the video and try this one on your own. Okay, so what I'm going to do is prime factor. I'm going to actually pull the -1 from the 2. And then the 16 you're going to start to learn has 4 2's in it. So if I combine all of these underneath the cube root, I have a -1 times 2, 2, 2, 2, and 2. I should have 5 2's total. Then for your m's, I've got 4 m's and 3 m's giving me m to the 7th, 1 n and 5 n's giving me n to the 6th. So you can take the cube root of -1, which is -1. So again, some people are just going to leave that underneath. I mean, you could, but I would pull it out. I mean, you can stick the cube root of -1 in your calculator and see what it tells you. It's going to tell you it's -1. And I'm looking for groups of 3. So this is coming out. So I have a -1, a +2. That's not enough for a group of 3, so those are going to stay underneath. And then we're going to apply the index rule. So 7 divided by 3 is 2, so I get m squared with 1 left over. 6 divided by 3 is 2, so I get n squared but with none left over. So underneath my cube root, I have 2 times 2 is 4, and then that leftover m. Then we have to multiply this together, so I get negative 2 m squared n squared cube root of 4m. That's it. So let's look at C. So this time the only difference is you've got something outside the radical. So you have to multiply what's outside the radical to what's outside the radical, which is nothing. So you're going to have a negative 3 out there. And then what's inside to what's inside. So I'm going to prime factor the 18 into 2 times 9 and then 3 times 3. So that negative 3 is already out in front previously. And then underneath the radical, I'm going to have a 2 from the left radical and then a 2 from the right radical and then 2 3's. And then I have x cubed and x to the 5th, so if you add those, you have x to the 8th. X squared and y squared, I keep saying x, y squared and y to the 8th. If you add those, you get y to the 10th. So I am looking for, so we already have a negative 3, I'm looking for groups of 2. So I'm going to pull a 2 out in front, multiply it to the negative 3. Pull a group of 3's out in front, multiply it. So there's no numbers left over. Divide this by 2, I get x to the 4th, no remainders. Divide this by 2, I get y to the 5th, no remainders. So there's not going to be anything left underneath the radical. So that's gone. Then we have to multiply what's out in front. So negative 3 times 2 times 3 is negative 18. And then we've got our x to the 4th and our y to the 5th. But we had an even root. So this isn't going to cause a negative, but this will. So I do have to put the y to the 5th in absolute value signs. And then this would be our final answer. All right, so let's look at example 4. Oops. So let me make this much bigger. Okay, so for example 4, we cannot have any radicals in the denominator. So if that happens, we're going to have to rationalize it. So for example 4, you're going to find that it works out pretty well. Remember that whatever's underneath a radical, I can cancel or reduce with anything that's underneath a radical because they have the same index. So if you can reduce first, I would. So because 50 and 2 are both divisible by 2, I'm going to divide both of them by 2. And when dividing like bases, you subtract where there are more. So I'm going to cancel 4 of those x's with 4 upstairs. So I end up with the square root of 25 x squared, and then there's nothing left under here, so it's the square root of 1, which is 1. So there's no reason to write it over 1. Now we can actually simplify this square root because the square root of 25 is 5, and the square root of x squared is x. Technically, we just took the square root of an even root, so we should put that in absolute values because that's an odd exponent and it could create a negative. All right, let's look at B. So you try B on your own, so pause the video and attempt to do B on your own. Okay, so I am going to reduce 45 and 5 by 5. So 5 divided by 5 is 1. 45 divided by 5 is 9. Then I'm going to subtract the x's upstairs. And so I'm left with the cube root of 9 x to the 6th. So although I can't take the cube root of 9 because 9 is 3 times 3, I can apply my index rule and divide this by 3. And so out in front is going to go an x squared, and underneath the cube root will stay the 9. And then that is your fully reduced answer. All right, pause the video and try C, and then turn it back on and see if you get the right answer. So I cannot reduce 81 and 16 like with each other, but I can cancel the x's and the y's, so I can perform that subtraction. So let's go ahead and do that. So I've got these x's are going to cancel with 2 there, and these y's are going to cancel with 3 there. So then that is going to leave you with the 4th root of 81. I'm going to prime factor 81. So 81 prime factored is 4 3s. And then we have x to the 3rd, y to the 8th, over. And then we have 16 is 4 2s, 4th root, and no variables. So now I'm looking for groups of 4. So I can take out a 3, pull it out in front, and remember I've got a fraction here. I can take out a group of 2s and pull that out in front, but then I have to apply my index rule. Well, I cannot divide 3 by 4 at all, so I'm not going to even bother, but I can divide 8 by 4. So I can divide the 8 by 4. So underneath my 4th root, up top, I have an x cubed, and then, oops, I didn't leave room, I have a y to the 2nd that's going to come out in front. So to rewrite this, I no longer have a radical in the denominator, so that's good. So then I have 3y squared, the 4th root of x cubed, all over 2. Now, once you do that, you have to look to see what's outside. Can you reduce anything that's outside? Nope. And then that's not simplifiable, so you're done. You don't have a radical in the denominator. Let's call it a day. So for example 5, you're going to actually find out that it's going to become a little bit more difficult. We're going to end up with a, I gotta grab a pillow so I can get my iPad a little higher there. Here we go. So you're going to find that you're going to be left with a radical in the denominator, so we're going to talk about how we're going to rationalize that. So as we look at example A here, we can still cancel the 5 and the 20. So we're going to start off with that. So 5 divided by 5 is 1. 20 divided by 5 is 4. And then we are going to divide like basis, so we will subtract where there are more, and this time there's more in the denominator. And that leaves us with nothing in the numerator except for a 1, and the square root of 1 is 1. So we have 1 over, and then we have the square root of 4, and then x. So we do have a radical in the denominator. 4 is a perfect square, so we could take the square root of 4 and it would be 2, but x is not a perfect square. So since our index is 2 and we have 1x, I need 1 more x in order to make it a perfect square. So I'm going to multiply this not by the square root of 4x, but just by the square root of x, because 4 is always already a perfect square. So if I multiply this by the square root of x, now I'm going to have 4x squared, and both of those are perfect squares, and then I can take the square root. What I multiply the denominator by, I have to multiply the numerator by the same thing. Otherwise, I don't have an equal fraction. So the numerator becomes the square root of x. The denominator becomes the square root of 4x squared. And now I can take the square root of 4x squared, which is 2x. Now, theoretically, because I just took the square root of an even root and the x is an odd root, I should put this in absolute values. And so this becomes your final answer. Let's look at B. So B is a cube root. So for right now, I cannot reduce the 7 with a 5, and the x and the y squared are not like bases. So there's really nothing I can do. 5 is not a perfect cube, and I cannot divide 3 into 2 because it doesn't even go in there once. So I have to rationalize the denominator. If I have an index of 3, I need perfect cubes underneath here. So to make 5 a perfect cube, I need 3 5s, and I need 3 y's. I currently have 1 5, so I need 2 more 5s to make it a perfect cube. So I'm going to multiply the bottom by 5 squared. Again, I have 1 5 underneath the radical right now. If I have 2 more 5s, it'll make it a perfect cube. So the y, I have 2 y's, so I only need 1 more y to make it, I'm trying to make that bigger, to make that a perfect cube. So then what I multiply the denominator by, I have to multiply the numerator by. So I'm going to multiply it by 5 squared y. And so I get 7 times 25 is going to be 175. So I get the cube root of 175. There are no perfect cubes in there because it's made up of a 7 and 2 5s. And then I have an x and a y. So none of those are perfect cubes. Then I'm going to divide by the cube root of 5 to the third, y to the third. So now I have perfect cubes underneath there. And if I apply the index rule, I can divide each of those by 3. And I get the cube root of 175 xy divided by 5y. And because it's an odd root, I don't have to worry about absolute value signs. All right, let's look at C. So C has some numbers outside of the radical, so you can reduce anything that's outside of a radical with what's outside and anything that's inside with what's inside. So let's start there. The 15 and the 3 are both divisible by 3, so 3 divided by 3 is 1, 15 divided by 3 is 5. And the 60 and 12 are both divisible by 12. So 12 goes into 12 once, and 12 goes into 60 5 times. Then there are more x's in the numerator, so this x cancels with one of those. And there are more y's in the denominator, so these 3 y's cancel with 3 of those. So we have a 5 in front, square root, 5 underneath, x to the 4th, and then in the denominator we have the square root, and we have y, just y. So now we have to rationalize that denominator, and because it's a square root, the index is a 2, I need 2 y's underneath here. I already have 1 y, I need 1 more. So I'm going to multiply by the square root of y and the square root of y. So I end up with 5 square root of 5 x to the 4th y all over square root of y squared. So, and don't go trying to reduce these, because then you're going to be back to what you had here. So I'm just doing some interim work here so you can see what I'm doing, but I'm going to actually take the square root of these now. I can't take the square root of 5, it's not a perfect square, but I can use my index rule here, and I can divide this 4 by a 2. Whoops, I wanted red. Divide this 4 by a 2. The y's to the first power, I can't divide that by 2, so that's going to have to stay there. But look at the denominator, it's now a perfect square. I can divide that by 2. So we end up with 5 I'm going to be able to bring an x squared out in front. And then we have left underneath the square root of 5 and a y, all divided by y. The last thing you have to make sure you do is look right here to see, is there anything I can cancel, because now they're all outside and they have nothing in common. Technically, I just took a square root of an even number, so I should have absolute values around this y. I don't need them around the x squared because this is an even exponent, and even if x were negative, squaring it would make the negative go away. So I am going to put absolute value signs here, and then this ends up being my final answer. And then if you want to look at this word problem, I skipped it in class. It's really not that big of a deal. You're basically just plugging in values into this and simplifying. So I'm not going to worry about that. So if you have questions on your homework, feel free to text me. Have a great day.